Uh, Today I present section 2 in the book. The big O and the little o locations. Yeah, in applied math, we often use these two locations. Then take a look at the definitions. Mathematics definitions are the most important definition. Definition. Let F and G be two functions. BO and little o locations compare two functions. When we write the following location, function f is big O of function t as x approaches x star. Okay. What this notation means? It means when there is a constant c and a neighborhood of x star. What it means? A neighborhood of x star. Yeah. This is a number 9. Yeah, number 9 is x star. Here. A neighborhood means some interval that contains this point. If this point is infinity, yeah. If this point is infinity, if x star is infinity, then a neighborhood of infinity means yeah, the interval. Yeah, a neighborhood for infinity is all the points greater than some number. Yeah. Then, yeah. Say for example, 100 infinity. This is a neighborhood of infinity. If we can find a constant c and a neighborhood of h star, x star, such that f in absolute value is bounded by c times absolute value of g. Yeah, such that this is a host in the neighborhood. Yeah, neighborhood. Is the definition clear to you? Huh? If we can find some number, this is a positive number, and a neighborhood of this point, so that is inequality holds, then we write f is BO of G as x approaches infinity. Approaches x star. Definition. Then what is little o? Number 2. We write f of x is little o of G of x as x approaches x star. When f over t as x approaches x star, okay, approaches t. If this limit holds, then we write f is little o of t. When this limit holds, we have, okay, when this limit holds, we have f of t in absolute value close to 0. Okay. When x is near the point x star. This limit implies when x is close to x star. There is a neighborhood of x star. Yeah. Function n compared to function t, very, very small. Yeah. Also, we can write this f far less. Yeah, this location, double less means far less, much less. T of x. Yeah. Hopes in a neighborhood of x star. Yeah. BO means this in means function f is bounded by c times t in the neighborhood. Little o means function f is much smaller than function t in the neighborhood of x star. Yeah, take out some examples. Let me show you examples. Yeah. Example. Then example 1. Compare these two functions. Function m is x to -2. Function t is x to -1. Okay. Compare these two functions. Now, function m over function t is x -2. X. This is x -2 moves to the top, and x -2 to the bottom. So 1. Now, when x approaches infinity, okay, as x approaches infinity, f over t approaches 0. So we have f is little of t as x approaches infinity. Yeah. This is what is f? X to -2. So x to -2 is little o x to -1 as x approaches. That means that when x is very large, x squared x to -2 is much less than x to -1. Little much less. Much. On the other hand, let's consider G over A. G over A, it is x negative 1 over x negative 2. This is move x negative 2 to the top, x negative 1 to the bottom. So I get x. Right, now I can see that when x approaches 0, G over F approaches 0. Approaches 0. Right. So I can write, so G is little o F as x approaches 0. What is G? X to negative 1. X to negative 1 is little o x to negative 2 as x. So specify this point, very important. Yeah. At 0, x1 is little o of x to negative 2. At infinity, x to negative 2 is a little o of x to negative 1. When x is very large in the neighborhood of infinity, x to negative 2 is much less than x to negative 1 in absolute. Yeah, they say that again. In a neighborhood, very small neighborhood of 0, x to negative 1 much less than x to negative 2 in absolute value. Little o, much less. BO, bounded by. Secondly, this is an example 1. Okay. Specify x star. This is the x star. Okay. Important. Okay. Okay. Now, example 2. Compare these two functions. Yeah. Function f is sine of x minus x plus 1 over 3 factorial x to the third. Yeah. What is function g? Yeah. X to the 1 to the 5th function g, right? Something. Now, solution. By Taylor's theorem, I can expand the function sine again. Taylor's theorem. Expand the function sine and the point zero. Okay, C is here. Yeah. So this is the sine zero. Go back to the Taylor's theorem. Sine zero. Then cos 1 over 1 factorial. Derivative of the function, then evaluate the derivative as 0. Then this is a 1. Okay. Yeah. Derivative of sine, cosine, evaluate as 0, 1. Then x minus c. Now c is 0. X is 0. Third term. Take derivative twice on function sine. Twice. Then we get once is cosine. Take derivative again, negative sine. Then evaluate as 0. So 0. Third term is so yeah. By Taylor's theorem, we get this polynomial x minus 1 over 3 factorial x 3. That plus error term, where the error term is, we have a formula for error term in Taylor's field. This is a 1 over 5 factorial times cosine some point theta times x per 3. What is theta? I don't know. I just know theta between 0 and x. Between 0 and x. This is what I know. This equation, left side is a curve. Right side, polynomial. Plus here. Take this. All right, now let me compare these two functions, f and g. Yeah, actually, this equation holds for, this equation holds for any x. In Taylor's theorem, choose the interval a to b as negative infinity to positive infinity. And the point c, set the point c to 0 in Taylor's theorem to get this equation. All right, now let me compare these two functions. Right. Our function is sine x minus x plus 1. Yeah. This is a function n. Right. Here, actually, I move these two terms to the left side. Then I get function n. Yeah. Move this to left side. Move this to left side. I get function. So this is equals to absolute value E4. And what is E4? E4 is here. So this is absolute value 5 factorial cosine theta times x 5. Yeah. So absolute value 1 over 5 factorial absolute value cosine theta times absolute value x 5. Cosine log greater than 1 absolute value. Cosine is always between -1 and +1. So less than. Yeah, this is some constant times function g. Okay. What is x? Actually, x is, this inequality holds for any x. For any x. Yeah. Function n is bounded from above by a constant times function g on this interval. So I can make the following statements. Okay. So number one, I can say that function f is big O of function g as x approaches infinity. One, because this inequality holds for on this interval. If I view this interval as a neighborhood of infinity, then I can make this statement. As x approaches infinity, f is big of g. Can you understand this? Just follow the definition. And also I can make this statement. F is big of g as x approaches, say, some finite number, for example, number 3. For number 3, I can find a neighborhood, such that function n is bounded by a constant times function g. And also I can say that function f is bit of t as x approaches negative. If I view this interval as a neighborhood of negative infinity, then I make this statement. Yeah.
Number 2 is very easy. 3 or just chosen.
Any number actually, choose a negative 100. Negative 100, yeah. This is a neighborhood of negative 100. Over this neighborhood, function n, log greater than, it is bounded from above by a constant times g. This is a big O rotation. Now, how about little O rotation? Here, let me erase. By Taylor's theorem, we have this equation always for any x. This is true. In Taylor's theorem, I said the interval a to b to be negative infinity to positive infinity. The point C is 0. Then now, this is about big O, little O. Okay, little O. Little O. Also compare these two functions. Not decide, not compare these two functions, but compare. Okay. Let me erase function g. Okay. Number 8. Okay, 1. Okay. Compare function f and g. What is g? X to the 4 as x approaches 0. Yeah. In a small neighborhood of 0, compare these two functions. Now, little o. Function f over this g as x approaches 0. Let me see. This is a sine function f over g x to the 4. Okay, now use this equation. Move x to the left side. This term to left side. It turns out that function f is equal to E4x over x. What is E4? Yeah. X approaches 0. 1 over 5 factorial. Cosine theta. Then x to the 5th. Then over x4. Cancel x to the 4. So limit 1, 5 factorial. Cosine theta times x. So 0. x approaches 0. So in a neighborhood of 0. So in a neighborhood of 0, f is little o of t. Yeah, as x approaches. When x is small, function f much smaller than function t in absolute because the ratio approaches. Yeah, this is a compare function f with x to the 4. If I compare function f with x to the 6, okay, yeah, up to yeah, in this example. Okay, now let me compare this function f with x to the 6 exponent. Then I let x approaches negative infinity. Now I compare this limit negative infinity. Negative infinity. Function t now is x to the 6. This is a negative infinity. 6. And now x per 3 divided by x to 6. So this is a x now approaching negative infinity. So 0. Now I write this time. Function f is little o of function t as x approaches negative infinity. That means when x is close to negative infinity, function f much less than function t in absolute. Little o, much less. Yeah. Example 3. Example 3. Example 3. We are given a series. Consider the series e to tangent x is 1 plus x plus x squared 2 factorial 3x to the third 3 factorial and 9x 4 factorial and so on. Okay. Consider this series. Okay, now retaining 3 terms. Yeah. 3 terms. First term, second term, the third term. Retaining these 3 terms. Estimate the remaining series using little o rotation. Okay. When we talk about little o, big O, we need to specify the point x star, x approaches x star, which point for x star? Here is as x approaches 0. Okay. 0 is x star. Okay. Consider neighborhood about 0. The remaining series, yeah, this part is remaining series. Write the part in little o location. Yeah. Right. Little o, we need to compute a limit. Okay. Yeah, let me compute. 3 x 3 factorial. Yeah, remaining series. Absolutely. I compare remaining series with some function. Okay, with which function? I think x to 2, okay, x to x squared. Because I want this approach to 0, right? As I compare, I let x approach to 0. Then, can you see that this is a 0, 1. The y value is 0. In the series, I take out x product, take it out, then times 3 factorial plus 9 x 4, and so on. And then over x squared. So I can cancel, okay? Cancel. Then what I get is x absolutely. Right. Now x approaches 0. Do you agree the limit is 0? Because x go to 0, and this sum approaches this number, the leading number, 3 over 3 factorial. Okay. Therefore, in the neighborhood, x approaches 0. In the neighborhood of 0, very small neighborhood, the remaining series much smaller than x squared. So therefore, I can write the remaining series. Yeah, is little of x squared. Specify as x approaches 0. This is true only in a neighborhood of very small neighborhood of 0. Okay, now this part roughly is little of x squared. Therefore, I can write this equation as E tangent x is 1 plus x squared. So plus little of x squared. Okay, now this is part A. Part B. Write the remainder in terms of BO. Okay? BO. Yeah. Part B. Yeah. Same person. Part B. Yeah. Cool. Number 2. Yeah. Any questions? Yeah. Let me change. Okay? consider the same series and keep the first three terms. Now, remainder. Estimate the remainder series, now this time, using BO notation. Not little o. Little o means much, much less. BO, not much less. There's a boundary. Also, no, I consider 0, okay? X opposite 0. I also consider X opposite 0. Okay. Now this time, not compute limit, okay? Not compute limit, but find a bound, okay, on function A. Yeah, this is a remainder. Remaining series. Remaining series. I want to find a bound for remaining series. Okay, now this is equals to, let me take out x to the, take x to the out. Nine x 4. Then the next term should be the power should be x to the 5. Okay, and do you agree? Yeah, I am consider x approaching 0. So take a neighborhood about 0. Do you agree? This is a less than equal to x very small, very close to 0. So pass, yeah, second term and the terms after the second term all contain x. Now I make x very small. So this part log greater than, say, for example, pick a number because this part go with 0. So pick a number 3. Arbitrary pick. Then x in a small neighborhood. Of 0. Yeah, x star is. I can always take a neighborhood about 0 so that this sum log greater than a number because of the sum go to 0. Now, remaining series is bounded by a number times this function. So, conclusion is, so remaining series is a bit of this function as x opposite 0. When x is very small, very close to 0, remaining series is bounded from above by a constant times x. Okay, now I can write remaining series as big O x as x approaches. Okay. The definition is about general functions f and g. Yeah. General functions compared to general functions in the neighborhood of some specific point x star. How about we have a sequence of numbers? Yeah. A sequence. A sequence, we can view it as a function. Can be viewed as a function. Which function? F of n independent variable is n is equal to hn. This function, the domain is independent variable assumes values from 1, 2, 3, 4, and so on. This is the domain. Because a sequence is a function, so I can apply the bit O and bit O location to sequence. Then what is X star for a sequence? Sequence n always approaches infinity. So star. No other choice, just infinity. That's n approaches. Now, take a look at two examples. Yeah. Example. Yeah. Consider this sequence and this sequence. I compare these two sequences in the neighborhood of infinity. Which one is larger? Yeah. Yeah. Okay. Now, n plus 1 over n squared. Yeah, this sequence. Let me rewrite this sequence as n plus 1 n times 1 n. Yeah, you agree? This is a less than or equal to 2 times 1. Actually, this is true for any n. For any n, this is true. So, a neighborhood of infinity, I can choose all the n's as a neighborhood of. So, in the neighborhood, this is bounded by a constant times this. So I can write. So we can write n plus 1 over n squared is a bit O of 1 over n. Of course, as n approaches infinity, only one choice for n. Little n. Example 2. Example 2. consider, I want to compare e to negative n this sequence and 1 over n squared this sequence. For n, no choice. N must be approaching infinity. This example about BO, now this time about little o. Little o, we need to compute a little bit. Let me compute this thing. Let me n over 1 over n. Of course, n approaches infinity. Now, again, now let me rewrite the quotient. N squared, move it to the top. E to negative n, move it to bottom. So n squared e n. This limit is 0. How to see this limit is 0? Log to full. Take derivative on n squared with respect to n. Take derivative on e to the n with respect to n. Log to full. Then take derivative. 2n. Then en, right? Take derivative log to full again. So this is the n approaches infinity. So 2 en. So you will see here. Now I can clean that. I can clean that. E to the negative n is little o. 1 over n squared. Of course, n goes to infinity. That means that when n is very large, I can find a neighborhood of about infinity. When n is very large, e to negative n much smaller than 1 over n. Little o much smaller in the neighborhood of infinity. In some neighborhood of infinity. Little o, big O. When if you are from engineering, you should be able to encounter these two relations. Let's start here and see you on Monday. This weekend I will post the first written homework. Now I have sufficient materials to assign the first written homework. I time the homework problems. The solutions, you can handwriting the solutions. You can time the solutions. And then take a photo or scan the solutions in PDF file. Upload your solution to Courses. I will grade on Courses. I will email you, this weekend about the detail how you do that.